Hello, calculus fans. This time we're going to use Stokes Theorem to help us compute a surface integral. So let's use Stokes Theorem to evaluate the surface integral of curl of f dot ds. And here f is going to be the vector field with components 2y cosine z, e to the x sine z, and x e to the y. And then s is going to be the hemisphere centered at the origin, radius 3, and we're going to take the top half of the sphere and we'll orient that sphere upward. Now we're going to avoid ever computing the curl of f since we're going to apply Stokes Theorem. So what we need is a parameterization of the boundary curve of S. And that boundary curve is simply the positively oriented circle in the xy plane of radius 3 centered at the origin. We've talked about that parameterization many times. We'll just use this parameterization. So r is going to be 3 cosine theta, 3 sine theta, 0. And of course theta goes all the way around 0 to 2 pi. What we'll do now is compute the surface integral of the curl of f by computing a line integral of f. And that's what Stokes Theorem tells us to do. Note that r prime is negative 3 sine theta, 3 cosine theta, 0. Now, if we plug in the parameterization into our vector field, we'll get this. F is equal to 6 sine theta, 0, 3 cosine theta times e to the 3 sine theta. So, according to Stokes' theorem, we know that the surface integral of the curl of f is equal to the line integral of f along the boundary curve. So we set all this up. We figured out what f was as a function of the parameter variable, and we also have r prime. So we dot those together and integrate from 0 to 2 pi. It's pretty nice. Almost everything cancels out. All we get is the I components multiplied together, so we get the integral from 0 to 2 pi of negative 18 sine squared theta d theta. And that just works out to negative 18 pi. Okay, that's all for now.